Hi, I'm an old guy and I do maths. Today we're looking at the second derivative. What is it? What's it used for? Well, let's answer the first question first, and we can answer that fairly simply. If we take a function of x equals x cubed, the first derivative of that is 3x squared, and I hope that that's uncontroversial. The second derivative is the derivative of this. So basically you're going through the process of differentiation twice to get to this. And you can see that we move from a cubic to a quadratic to a linear function in this case. Now, I'll just say this as an aside really. In a more complex cubic, it's really easy to find the point of inflection by getting to the second derivative and solving that for zero. It's kind of useful. There will always be, in the case of a cubic, only one solution. Now, other forms of notation for this. If we look at this, this is the traditional notation, or one of the traditional forms of notation for the derivative. This is the second derivative here, d2y dx2. And when you see this, it corresponds to this. Now, what does this get used for principally? Well, again, let's go back to these and just see what this does. This gives us a rate of change. So if we want to find, for instance, again in a more complex cubic, if we want to find the maximum, the local maximum and local minimum, the turning points, if you will, we differentiate and solve this for zero. If we want to find the gradient at a particular point, we insert the x value of that point into this and we get the gradient. And that's true for any function. I'm not just talking about cubics here, but just for the purposes of today's talk, I am going to concentrate on cubics. Now, so if this gives us a rate of change, what does this give us? Well, it gives us the change of a rate of change. It gives us acceleration. Something that may or may not be useful depending upon what you're doing. Physicists, of course, I think will find this useful. So, what does it tell us about the speed of something and how it changes, and why does it tell us that? Well, if we think about what happens when we derive a function, so let's just do this. So there's our original function. Here's our derived function of that. Here we are, 3x squared. Now, down here we have the turning point of this function. It also tells us where the gradient on this is 0, which happens to be at the point of inflection. And if we needed to confirm that, we could go to this. Now, if we derive this, what we're looking at is we're looking at the difference of y over the difference of x. It just so happens that it's the second derivative because it's the next one in line to this. And what we get, of course, is we get a linear function. Function of x in this case is 6x, 3x squared, x cubed. So what this line tells us, what this line gives us, is the rate of change in this graph at any point. So for instance here, what is the rate of change here? Well, we can work it out from this function if we know the x value of this. So think about that for a moment. We are looking at a graph of rates of change. When we're looking at the change in the rate of change, what we're looking at is acceleration or deceleration if this thing were upside down. And that is the key takeaway of the second derivative. That's what it does. Now, it's not difficult to calculate. It's just another piece of differentiation. If you can do the first differentiation to get to dy on dx or f prime, if you can do that, it's a pretty reasonable assumption that you can do this. It might get a little interesting around things like logs and trig functions, but it's not an insurmountable problem at all. What you'll find is that you'll just move backwards and forwards, for instance, through sines to cosines and back to sines. But that's by the by. It will do the job, and it will give you a function that will tell you the acceleration on a particular point on your original graph. Thank you very much for watching. I hope that this was useful. If you did find it useful, please like and subscribe, and I'll see you next time. Bye.